Welcome back. Whew, we're in an exciting streak of videos coming up here. I mean, the whole course is fun, trust me, but this is really exciting because training your first machine learning model seems a little bit like magic, but it's even more fun when you're writing the code yourself, what's going on behind the scenes. So we discussed that the whole concept of training is from going unknown parameters, random parameters, such as what we've got so far, to parameters that better represent the data. And we spoke of the concept of a loss function. We want to minimize the loss function. That is the whole idea of a training loop in PyTorch, or an optimization loop in PyTorch. And an optimizer is one of those ways that can nudge the parameters of our model, in our case, weights or bias, towards values, rather than just being random values like they are now, towards values that lower the loss function. And if we lower the loss function, what does the loss function do? It measures how wrong our model's predictions are compared to the ideal outputs. So if we lower that, well, hopefully we move these red dots towards the green dots. And so, as you might have guessed, PyTorch has some built-in functionality for implementing loss functions and optimizers. And by the way, what we're covering so far is in the train model section of the PyTorch workflow fundamentals. I've got a little nice table here which describes a loss function. What does it do? Where does it live in PyTorch? Common values. We're going to see some of these hands-on. If you'd like to read about it, of course, you have the book version of the course here. So, loss functions in PyTorch. I'm just in docs, torch.nn. Look at this. Look at all these loss functions. There's far too many for us to go through all in one hit. So we're just going to focus on some of the most common ones. Look at that. We got about, 15 loss functions, something like that? Well, truth be told is that which one should you use? You're not really going to know unless you start to work hands-on with different problems. And so in our case, we're going to be looking at L1 loss. And this is, again, once more, another instance where different machine learning libraries have different names for the same thing. This is mean absolute error, which we kind of discussed in the last video, which is if we took the distance from this red dot to this green dot and say it's 0.4, thereabouts, 0.4, 0.4, and then took the mean, well, we've got the mean absolute error. But in PyTorch, they call it L1 loss, which is a little bit confusing because then we go to MSE loss, which is mean squared error, which is L2. So naming conventions just takes a little bit of getting used to. This is a warning for you. So let's have a look at the L1 loss function. Again, I'm just making you aware of where the other loss functions are. We'll do with some binary cross-entropy loss later in the course. And maybe even, is there categorical cross-entropy? We'll see that later on. But all the others will be problem-specific. For now, a couple of loss functions like this, L1 loss, MSE loss, we use for regression problems. So that's predicting a number. Cross-entropy loss is a loss that you use with classification problems. But we'll see those hands-on later on. Let's have a look at L1 loss. So L1 loss creates a criterion. As I said, you might hear the word criterion used in PyTorch for a loss function. I typically call them loss functions. The literature typically calls it loss functions. That measures the mean absolute error. There we go. L1 loss is the mean absolute error between each element in the input X and target Y. Now, your extracurriculum, as you might have guessed, is to read through the documentation for the different loss functions, especially L1 loss. But for the sake of this video, let's just implement it for ourselves. Oh, and if you want a little bit of a graphic, I've got one here. This is where we're up to, by the way, picking a loss function optimizer for step 2. This is a fun part, right? We're getting into training a model. So we've got mean absolute error. Here's that graph we've seen before. Oh, look at this. Okay. So we've got the difference here. I've actually measured this before in the past, so I kind of knew what it was. Mean absolute error is if we repeat for all samples in our set that we're working with, and if we take the absolute difference between these two dots, well, then we take the mean. We've got mean absolute error. So MAE loss equals torch mean. We could write it out. That's the beauty of PyTorch, right? We could write this out. Or we could use the torch NN version, which is recommended. So let's jump in. There's a colorful slide describing what we're about to do. So let's go set up a loss function. And then we're also going to put in here, set up an optimizer. So let's call it loss fn equals nn dot L1 loss. Simple as that. And then if we have a look at what's our loss function, what does this say? My goodness, my internet is going quite slow today. It's raining outside, so there might be some delays somewhere. But that's all right. It gives us a chance to sit here and be mindful about what we're doing. Look at that. Okay, loss function. L1 loss. Beautiful. So we've got a loss function. Our objective for training a machine learning model will be to, let's go back, look at the colorful graphic, will be to minimize these distances here, and in turn, minimize the overall value of MAE. That is our goal. If our red dots line up with our green dots, we will have a loss value of 0, the ideal point for a model to be. And so let's go here. We now need an optimizer. As we discussed before, the optimizer takes into account the loss of a model. So these two work in tandem. That's why I've put them as similar steps if we go back a few slides. So this is why I put these as 2.1. Often picking a loss function and optimizer in PyTorch come as part of the same package because they work together. The optimizer's objective is to give the model values, so parameters like a weight and a bias, that minimize the loss function. They work in tandem. And so let's see what an optimizer. Optimizers, where might that be? What if we search here? I typically don't use this search because I prefer just using Google search, but does this give us optimizer? Hey, there we go. So again, PyTorch has torch.optim, which is where the optimizers are. Torch.optim, let me put this link in here. This is another bit of your extra curriculum if you want to read more about different optimizers in PyTorch. As you might have guessed, they have a few. TorchOptim is a package implementing various optimization algorithms. Most commonly used methods are already supported, and the interface is general enough so that more sophisticated ones can also be easily integrated into the future. So if we have a look at what algorithms exist here, again, we're going to throw a lot of names at you, but in the literature, a lot of them that have made it into here are already good working algorithms. So it's a matter of picking whichever one's best for your problem. How do you find that out? Well, SGD, stochastic gradient descent, is possibly the most popular. However, there are some iterations on SGD, such as Atom, which is another one that's really popular. So again, this is one of those other machine learning is part art, part science, is trial and error of figuring out what works best for your problem. For us, we're going to start with SGD because it's the most popular. And if you were paying attention to a previous video, you might have seen that I said look up gradient descent. Where have we got this? Gradient descent. There we go. So this is one of the main algorithms that improves our models. So gradient descent and backpropagation. So if we have a look at this, stochastic gradient descent, a bit of a tongue twister, is random gradient descent. So that's what stochastic means. So basically, our model improves by taking random numbers, let's go down here, and randomly adjusting them so that they minimize the loss. And once our optimizer, that's right here, once our optimizer, torch.optim, let's implement SGD, stochastic gradient descent. We're going to write this here, stochastic gradient descent. It starts by randomly adjusting these values. And once it's found some random values or random steps that have minimized the loss value, we're going to see this in action later on, it's going to continue adjusting them in that direction. So say it says, oh, weights, if I increase the weights, it reduces the loss. So it's going to keep increasing the weights until the weights no longer reduce the loss. Maybe it gets to a point at, say, 0.65. If you increase the weights anymore, the loss is going to go up. So the optimizer is like, well, I'm going to stop there. And then for the bias, the same thing happens. If it decreases the bias and finds that the loss increases, well, it's going to go, well, I'm going to try increasing the bias instead. So again, one last summary of what's going on here. A loss function measures how wrong our model is, and the optimizer adjusts our model parameters, no matter whether there's 2 parameters or millions of them, to reduce the loss. There are a couple of things that an optimizer needs to take in. It needs to take in as an argument params. So this is, if we go to SGD, I'm just going to link this as well. SGD, there's the formula of what SGD does. I look at this and I go, there's a lot going on here. It take me a while to understand that, so I like to see it in code. So we need params. This is short for what parameters should I optimize as an optimizer. And then we also need an LR, which stands for, I'm going to write this in a comment, LR equals learning rate. Possibly the most, I didn't even type rate, did I? Possibly the most important hyperparameter you can set. So let me just remind you, I'm throwing lots of words out here, but I'm kind of like trying to write notes about what we're doing. Again, we're going to see these in action in a second. So check out our models and parameters. So a parameter is a value that the model sets itself. So learning rate equals possibly the most important learning hyperparameter. Oh no, I don't need learning there, do I? Hyperparameter. And a hyperparameter is a value that us as a data scientist or a machine learning engineer set ourselves. You can set. So the learning rate is, in our case, let's go 0.01. You're like, Daniel, where did I get this value from? Well, again, these type of values come with experience. I think it actually says it in here. LR 0.1. Yeah, okay, so the default is 0.1. But then if we go back to opt-in, I think I saw it somewhere. Did I see it somewhere? 0 point something, 0? Yeah, there we go. Yeah, so a lot of the default settings are pretty good in Torch optimizers. However, the learning rate, what does it actually do? We could go 0.01. These are all common values here. 0001. I'm not sure exactly why. Oh, model, it's model 0. The learning rate says to our optimizer, yes, it's going to optimize our parameters here, but the higher the learning rate, the more it adjusts each of these parameters in one hit. So let's say it's 0.01 and it's going to optimize this value here. So it's going to take that big of a step. If we changed it to here, it's going to take a big step on this 3. And if we changed it to all the way to the end, 001, it's only going to change this value. So the smaller the learning rate, the smaller the change in the parameter. The larger the learning rate, the larger the change in the parameter. So we've set up a loss function, we've set up an optimizer. Let's now move on to the next step in our training workflow, and that's by building a training loop. Far out. This is exciting. I'll see you in the next video.